In this particular example, we are given a force system as shown here. There are 4 forces, 3 of them are known. The 4th one is not known, neither is its angle known. The find statement here says determine F required for static equilibrium. I'm going to write in green here. This is not something you would typically write in your notes, but I want to point something out here. I want you to note that F is assumed. What this means is F is shown in the diagram because when we're dealing with a problem like this, we have to have a way in which to determine positives and negatives. However, we don't actually know which way this force is going. So here we are assuming its direction. We could be correct or incorrect. And as we continue to solve this problem, the signs on our answer will let us know whether we were right or wrong. The first step of our solution is to draw a free body diagram. In this case, I'm calling this free body diagram A. You can call it whatever you want. The first thing we always need in our diagrams is a sign convention. Although I won't count points this way, technically, if you don't have a sign convention, everything else in the problem is wrong, because the sign convention determines the signs of all these answers. What you need to next do is label all the forces. So I'm going to call this 100 Newton force F1. The 60 Newton force I will call F2. And the 30 Newton force is F3. We also need to label angles, and this 50-degree angle I'm going to call alpha. The reason I chose alpha for this 50-degree angle is because it goes with F1. At this point, all of my forces and angles are labeled in my free body diagram, and I can continue on to step 2. It's perfectly acceptable to abbreviate static equilibrium, but the statement here should be applying static equilibrium to x, or applying static equilibrium to the x direction. The first thing you need to state is the sum of the forces in the x direction equals 0. This is the assumption that we are making on this problem. All of our math and work here is going to be based on this statement. I will always be looking for this statement. If you do not state static equilibrium, you are going to lose points, because as I said, that is an assumption that we are applying to this particular situation. If that assumption is not true, if the object is not at static equilibrium, none of the rest of the math is going to be correct. After stating static equilibrium, then we state what I call our 0 statement, which includes all of the forces. So 0 equals Fx plus F1x plus F2x plus F3x. After our 0 statement, we need to have a where block. In the where block, I'm going to define what each of these particular components are. So Fx equals, look back up at the diagram, the x component of the force F would be in the negative direction, because I've defined it as negative. And the value of Fx would be cosine of phi times F. Next we have F1x, and F1x is acting in the positive direction. And the value of F1x is cosine alpha times F1. Then we have F2x. F2 is also acting in the positive direction, and the value of F2x is simply F2. Finally, we have F3x, and since F3 has no x component, its value is 0. This line is still required even though F3x is equal to 0. After that, we plug all of those values back into our 0 statement. For each line of this equation, you want to see where you have fewer unknowns. So for example, for this first term, we're going to plug something into this equation. On the right-hand side of this equation, I actually have 2 unknowns. I don't know phi, and I don't know f. On the left side of the equation, I don't know fx, so it makes more sense to use that side of the equation. Make sure that you keep the negative sign from this statement when you plug it into the 0 statement. After that, everything else will be from the right side because we know all of these values. Now, if you wanted to, you could also write plus 0 at the end here, but that's not necessary. So now we have an equation with one unknown. Whenever you have an equation with one unknown, just go ahead and solve it. I'm going to solve this equation for fx. Remember that you must properly algebraically develop each equation before plugging any numbers in. So then fx equals, now I can plug my numbers in. So fx equals positive 124.279 newtons. This positive sign is required. I will be looking for that, and you will lose some credit if I do not see a sign of some type. Once again, what I'm writing in green here is just for notes. This would not actually go in the GFSA format. This sign does not indicate direction. It indicates agreement or disagreement. In this case, it indicates agreement with the diagram. That indicates that yes, the x component of f is indeed going in the negative direction. Although it's a positive sign, it indicates our assumption was correct. The very next statement line you should have is fx equals 124.279 newtons going in the negative x direction. It is important to include this last line because the sign could be a little confusing to someone who's not actually used to this method, or even to someone who's casually looking over the problem. Whenever we use static equilibrium to solve for an unknown, the sign on the answer will indicate whether we were correct or incorrect in our assumption, and not the actual direction. The next step would be to do the same thing in the y direction. In this case, we would say sum of the forces in the y direction equals 0. Remember that we need to start by stating our assumptions. 0 equals F1 y plus F2 y plus F3 y plus F y. Once again, we need a where statement. F1 y equals a negative sine alpha times F1. F2 y equals 0, because F2 does not have a y component. F3y equals a positive F3. And Fy equals a negative sine phi times F. Plug all those values back into our 0 statement, so we get 0 equals F1 was negative sine alpha times F1. F2y we don't have to write because it is 0. F3y is plus F3. And once again, when we're looking at this last line here, which side of the equation has fewer unknowns? Well, the right has 2 unknowns, phi and f. The left only has 1 unknown. So I will use the left, minus Fy. Now we can solve for Fy. Fy equals a negative sine alpha times F1 plus F3. And once we plug our values in, we find that Fy equals a negative 46.6044 newtons. Remember that this negative sign does not actually tell us direction, but it indicates disagreement with the diagram. So then our final step is to write Fy equals 46.6044 newtons going up. My reasoning behind showing you this particular example is to show you this sign discrepancy. You will see that the negative sign here actually indicates that the y component is going up. The reason for that is we initially assumed the y component of f going down. So negative, once again, here indicates disagreement with the diagram. I have now drawn a working diagram illustrating the actual direction that Fy and Fx are going. Using the parallelogram rule, I can draw a projection of Fy from the tip of Fx, can draw a projection of Fx from the tip of Fy, and the resultant is going to bisect that parallelogram. This diagram is optional, however, I find it to be useful. So now we can say solving for phi and f. Since this is a right triangle, f equals the square root of fx squared plus fy squared. And so we find F to equal 132.730 newtons. You will notice that I don't have a sign on that. This is strictly a magnitude. When you solve for F using this particular method, it doesn't matter what signs you had in Fx or Fy. You're squaring them, so they're going to come out positive. So this equation here will not tell you the sign, it will just tell you the magnitude, and you should not have a sign on there. Now, although we could use sine, cosine, or tangent to solve for phi, the best thing here to do would be to use tangent. And the reason I say that is because that reduces one more possibility for error. If I use sine or cosine, my answer here is going to be dependent upon getting F right. If I get F right, then I'll get phi right, but if I use F to solve for phi, I can possibly get both wrong. Using this method here with tangent, you are less likely to make that type of error. Plugging our values in, we find phi equals 20.5560 degrees. So then in our answer box, we would report both F and phi. F equals 132.7 newtons. Phi equals 20.56 degrees. Keep in mind, it's very important that you understand what the signs indicate. When we're solving using static equilibrium, the signs do not indicate true direction, rather they indicate agreement or disagreement with the diagram.